Hello everyone and welcome back. In this video, we're going to introduce the concept of simple harmonic motion and talk about Hooke's law. Let's take a moment to situate this topic. We've been talking about mechanics, which is the study of motion. We started with linear motion, which is motion in a straight line. A car traveling down the x-axis is an example of something in linear motion. Next, we talked about projectile motion. An object is in projectile motion if the only force acting on it is gravity. A golf ball hit from a tee is an example of something in projectile motion. Another category of motion is periodic motion, or motion that continually repeats itself after an equal interval of time. And we already discussed a few examples of periodic motion. For example, an object is in circular motion if it maps a circular path, such as the cars on a Ferris wheel. And an object is in rotational motion if it rotates about an axis, such as the Ferris wheel itself. And this unit is about oscillatory motion, which is a back and forth motion bounded by 2 points. And even more specifically, we're going to be talking about simple harmonic motion, which is a special type of oscillatory motion in which the restoring force is proportional to the displacement. And we'll talk about what this means in a few minutes. There are many phenomena that exhibit simple harmonic motion. Examples include the vibrating particles of a sound wave, electrons in a wire in an AC circuit, and even the seismic vibrations caused by an earthquake. Two classic examples that are commonly used to learn about simple harmonic motion include a mass oscillating on a spring and a pendulum swinging back and forth. Let's start by looking at a mass spring system in more detail. A horizontal mass spring system consists of a mass attached to one end of a spring, while the other end of the spring is attached to a fixed barrier, such as a wall. This mass spring system has the ability to oscillate back and forth. Unless specified, we assume that the mass is on a frictionless surface. When the spring is not stretched or compressed, the mass spring system is said to be at its equilibrium position. At the equilibrium position, the net force acting on the mass is 0. You can define the equilibrium position to be at the end of the spring, the end of the mass, or wherever you want, as long as you are consistent. I'm going to define the equilibrium position to be at the center of mass of the attached block for this example. When the spring is stretched or compressed, a new force called the restoring force appears in the spring. The restoring force exerts a force on the mass and aims to return the mass spring system to its equilibrium position. An object or system oscillates in simple harmonic motion if it obeys Hooke's law. Hooke's law states that the restoring force is proportional to the displacement from equilibrium. Hooke's law can also be written as an equation, F sub s equals negative kx, where Fs is the restoring force, k is the spring constant, which we'll talk about in a minute, and x is the displacement from equilibrium. Note that we are using the variable x to stand for distance or displacement in this unit. Hooke's law tells us that if we pull the mass a small distance x, the restoring force will be small. But if we pull the mass a greater distance, the restoring force will increase. So the statement, the restoring force is proportional to the displacement, means that the greater the displacement from equilibrium, the greater the restoring force stored in the spring. And in reverse, it also means that you cannot stretch a spring by applying a constant force. It takes a greater and greater force to continually stretch the spring a greater distance. As an example, let's say that I pull the mass 10 centimeters in the positive x direction. We'll call this x max. As I hold the mass, the restoring force is at a maximum, and the mass has elastic potential energy because when I let go, the restoring force will cause the system to oscillate between x min and x max. And since I pulled it 10 centimeters to the right of equilibrium, it will also move 10 centimeters to the left of equilibrium. Next, let's look at the negative sign. The negative sign tells us that the restoring force always acts in the opposite direction as the displacement. Note that if I pull the block in the positive x direction, the restoring force acts in the negative x direction. When you look at Hooke's law, it looks like the negative sign goes with the k, but it never goes with k. It indicates the direction of the force or the displacement. In this case, we have a positive displacement and a negative restoring force. But if I compress the spring, the displacement is now negative and the restoring force is positive. Because the negative sign only indicates direction, we often don't write it or use it in our calculations. Next, let's look at K. There are many different types of springs. The spring constant K is a measure of the stiffness of the spring. And just a side note, K is sometimes called the stiffness or force constant of a spring or metal bar. A spring with a large K value is a stiff spring, while a spring with a low K value is a looser or more stretchy spring. And K values can vary a lot. For example, the spring in the shock absorbers of your car might have a K value of 25,000 newtons per meter, while a much looser spring, like a slinky, might have a K value of 0.5 newtons per meter. We can determine the units of K by rearranging Hooke's law in solving for K. In this sense, we have force in newtons, displacement in meters, so the units of K are newtons per meter. This means that it takes 25,000 newtons to stretch this shock absorber 1 meter, and it only takes 0.5 newtons to stretch a slinky 1 meter. So in summary, how easily a spring stretches depends on its K value. When a spring is hung vertically, gravity may help elongate the spring. Regardless, the equilibrium position is the length of the hanging spring, taking into account any gravitational effects that are present. When a mass is placed on the spring, it's going to stretch even more, and the equilibrium position now changes to the stretched length of the spring caused by the mass. And again, how far the spring stretches depends on the spring constant of the spring. In many cases, the K value of a spring is given. Other times, we can use this initial stretch to calculate K. Let's look at an example. When a 2 kilogram mass is placed on a vertical spring, the spring stretches 25 centimeters. What is the spring constant of the spring? We can start with Hooke's law, and in this case, the weight of the hanging mass causes the spring to stretch and is therefore equal to the restoring force. So plugging in our values, we have a mass of 2 times 9.8 equals K, and it's stretched 25 centimeters, so I turn that into meters, and we have a K value of 78.4 newtons per meter. You should also be able to determine the spring constant of a spring experimentally. Doing an experiment will yield a more accurate K value than our previous example because it'll be based on more than one data point. Whenever you're asked to design an experiment, try to start with a known relationship if possible. In this case, we can start with Hooke's law. If we line Hooke's law up with y equals mx plus b, we can see that the experimental variables are force and displacement. And if we graph displacement on the x-axis and force on the y-axis, we can see that the slope of the line is going to give us K. And in addition, I now have a good start on my data table. Next, let's look at a possible apparatus. In this example, we have a ring stand, a rod on top from which we can hang the spring, and a meter stick. And we start the experiments with no weights on the spring. Let's pretend that this picture here is this section of the apparatus blown up. The first thing you want to do is note the equilibrium position of the spring. In this picture, the equilibrium position is defined to be the end of the spring, which we can see is 20 centimeters. And now we're going to collect our first set of data points. You'll also notice that I expanded the data table to make it easier to record our data. So we start by adding a 50-gram mass to the spring. When I do that, I'm going to record the data in the data table. So I have 50 grams, I converted that into kilograms, and then I converted that into newtons. And we can also see that when I added this 50 grams, the spring elongated. It stretched from 20 to 35, so it stretched 15 centimeters. But I have to convert that into meters, so 0.15 meters. It's the F and the X values that I'm ultimately interested in. In the next trial, I add another 50 grams. So I now have 100 grams hanging on the spring. So I'm changing 100 grams into kilograms times 9.8 to change that into newtons. And I notice that it now has stretched from equilibrium 20 all the way down to 50. So it has stretched 30 centimeters, converting that into meters, 0.3 meters. Notice that every time that I add mass, I'm always measuring the elongation from equilibrium. You can then continue adding more and more weights to the spring and recording the mass and the elongation until you fill your data table. But make sure that you don't add too much mass to the spring, that you permanently damage or deform the spring. You know you're okay if when you take off your mass, the spring compresses and goes back to its original equilibrium position. We can then graph the data, force on the y-axis and displacement on the x-axis, and find the slope of the best fit line. The slope of the best fit line is the spring constant. So the spring constant of our spring was 3.27 newtons per meter. It's also important to know that not all springs obey Hooke's law. A linear spring is one in which the graph of the restoring force versus displacement produces a straight line, like in our previous example. A nonlinear spring, however, may stretch or compress inconsistently and produce a graph that is curved. This graph was the result of repeating the lab that we just described using a rubber band instead of a spring. Rubber bands often behave as nonlinear springs. Sometimes they don't obey Hooke's law at all. Other times they obey Hooke's law over a small range of displacements, but deviate from the norm in other areas. The last thing we need to do is to make sure you recognize how your course defines simple harmonic motion. Because this topic is appropriate for students in a variety of different physics courses, the defining statement or equation may be different. So let's start with the basics. A mass spring system is in simple harmonic motion if the restoring force is proportional to the displacement and the restoring force acts in the opposite direction as the displacement. Or we could just say that something is in simple harmonic motion if it obeys Hooke's law, because each of these statements is part of Hooke's law. We could also say the same thing mathematically by saying an object is in simple harmonic motion if it moves according to the model F equals negative kx. This is the defining equation for AP Physics 1. It should also be noted that whatever is true about the force is also true about the acceleration from F equals ma. Since the mass is the same, if the force is proportional to the displacement, the acceleration is also proportional to the displacement. So simple harmonic motion can also be defined in terms of acceleration instead of force. We could write these statements mathematically as A equals negative kx. But a more common way to write the acceleration model is the acceleration equals negative omega squared x, which we'll learn about in a future lesson. This is the defining statement for IB physics. And if you're a calculus student, you may also understand this notation where the acceleration is written as the second order derivative of the position function. This is the defining statement for AP Physics C. It's most important that you understand the basic conditions of simple harmonic motion and recognize that each of these statements is a different way to say the same thing.